So, in the series of basics of software defined radios and practical applications, today we are discussing the topic of distortion parameters, and within this topic we are discussing nonlinear distortion. So, while talking about the distortion introducing elements in receiver, we were talking about noise figure of the ADC. In the last lecture we were discussing the noise figure of an ADC, and as an assignment it was given to the participant that the sampling rate is 100 megahertz, the bandwidth considered is 1 hertz, input impedance is of 200 ohm, and applied voltage input is 1 volt peak. It is to be noted it is not peak to peak, it is peak, and signal to noise ratio is of the system is given as 76 dBc. Now, if we put these values in this equation, we will get our solution as 24 dB. Now, it is quite high value, and if you calculate the corresponding noise factor by converting this dB back into the absolute form, you will get 15.84. Now, if you remember our previous example when we were calculating the noise figure of the whole system, if you see here the receiver portion was showing exceptionally high noise factor. So, we can say that what we are achieving here is actually matching with this data, and receiver because of the ADC is having very high noise factor. So, now moving on to the current distortion introducing elements in receiver, we will continue with the different architectures. So, if you remember, this is the heterodyne structure for our transmitter and receiver. In the transmitter receiver we have discussed the noise scenario, noise due to phase and IQ imbalance, DC offset, and all these parameters, and how they are related to different topologies. Now, let us have a look at the nonlinearity in the both of the transmitter and receiver paths. So, the nonlinearity in the path is mostly seen in the mixers which are used for the up and down conversion, and more than that we have amplifiers so that we can send our signal to a high level. So, those are called high power amplifiers. Apart from that, to maintain the level at the mixer input so that it is at the proper range of power, we have IF amplifiers in both transmitter and in receiver. Receiver side also we also have low noise amplifier, so that whenever we get the signal, the power which we have lost due to attenuation, that can be recovered, and this amplified signal is sent to the band pass filter. In filtering and all those applications, again some attenuation happens and our signal level drops. So, just before our ADC and DAC, we have to control this level again, and some kind of amplifiers are used here. As long as the non-linearity in the mixer is concerned, it leads to up conversion down conversion process. So, it is beneficial in this case. We have some unwanted components like harmonics, but that we can ignore easily because we are using filters before and after this component. Now, let us discuss the component of the amplifier, which is IF amplifier or high power amplifiers or low noise amplifiers. These amplifiers, when they have non-linearity, it is not a desired effect. We want our amplification to be linear. So, this undesirous thing we cannot actually completely avoid. Why is that? If you remember, when we started our discussion initially on the software defined radios, we have proposed the concept of pure digital RF front ends, and in this we have proposed that it is desirable that all the functionalities can be ported back to the DSP domain, and after that if possible we can directly do the D2A and A to D converter, and it will be very small portable device and it will be very reconfigurable. But what was the limitation? First limitation was A to D and D2A speed, but we have seen that we have methods like RF sampling, where we can directly do the sampling at the RF speed, and in that case we can actually avoid all these components like mixers and allos and additional filters. So, this first limitation is the modern scenario. We are able to actually reaching to a stage where we can actually avoid this problem. But the second one, the high power to transmit signal to long distances, we cannot avoid RF amplifier. Whenever we have to amplify any signal, we have to have an amplifier there. So, the power amplifiers the amplifiers which are actually used to power up the signal so that they can travel to a long distance. They are of two types. First is solid state power amplifiers, short form is SSPA, and the travelling to wave amplifiers, TWTEs. If we have a look at these two, the solid state power amplifiers are using transistors. They have medium nonlinearity, but they have memory effects. Memory effects means whenever you apply any signal, the output is not only the function of input, but the previous value of input also. So, that is why hence the name of memory effects. The additional advantage is that it is compact in nature. Wireless communication frequency range is its range of operation, and most of the mobile etc. they use this SSPAs because of their compact nature. Efficiency is medium, and also power level, output power level is medium, and it depends on different classes. So, solid state power amplifiers have different classes, and according to them it can be operated. It is mostly used for the mobile communication. Now, if we have a look at the travelling tube wave amplifiers, they are vacuum tube based electronic devices. They have much higher nonlinearity as compared to their SSPA counterparts. They does not have any memory effects. They are bulky in nature, but they have advantages such as they can be used for very high frequency. So, millimeter wave applications normally they can be used. They have higher efficiency with respect to the SSPA counterparts, and they can provide much higher power. Now, I want to clear here that even in the field of SSPA, the research is going on so that high efficiency and power can be achieved, but TWTAs are established in this field. They are mostly used for the long distance and satellite communication because they can send very high power, so it can go very far. So, it was just a comparison based on the outlook of these two amplifiers. Now, let us have a look at the non-linearity due to amplifier. Whenever we apply any input power, we want our output power which is proportional to the input power with some gain. So, if you look at this diagram, whenever we are applying minus 70 dBm power in the input, at the output we are getting almost or minus 60 dBm output power. So, there is a gain of 10 in between these two values, 10 dB gain this power amplifier is giving to us. Now, it is a good thing. If it is giving 10 dB amplification, then whenever we apply minus 60, we should be able to get minus 50, as we can see from here. For minus 40, we should get minus 30, and as long as it keeps doing this, it is working in a linear region, and we say that okay, amplification is happening properly. But when we are going to very high input power level, after some time our output is not proportional to the input and it becomes saturated, it becomes flat, it is being shown here. If we still keep increasing, if we still keep giving it enough power, then eventually it will burn out. So, when we start seeing the saturation power, we know that it is working at its peak frequency. Now, what is the problem in this scenario? As long as it is working in the linear region, there is no problem, but when it starts working in the non-linear region here, then we have problems. Now, here we are showing a nonlinear system where we are applying a signal at the input, and the output is shown in the y axis in this form. So, we can see that input wave, when it is a sinusoidal signal in the nature, when it is working in the linear range, the output is the amplified version and it is sinusoidal in the nature. But whenever the waveform is going towards the saturation region, then there is some clipping. So, for this region, when it is becoming saturated, it is becoming flat here because it not go beyond that, it is clipped there, and because of that our output becomes non-linear. It is not a linear function of the input anymore. Moreover, as we can see from the picture, we are losing some power here. If it would have been able to take the full swing, we would have gotten this waveform. So, we are losing this power. So, where does this waveform power goes? So, we will discuss that soon. Now, if you look at this diagram and the previous diagram of the PA characteristic, P in versus P out, we can say okay, let us just work in the linear range. Why we have to work at the saturation region at all? Now this is the limitation, we cannot work at the linear region, because when we see the curve of the efficiency with respect to the output power taken by the power amplifier, we can see that distortion keep increasing with the output power. So distortion is minimum here, and at this region it might be possible it is only because of the noise and not the non-linearity. But if you look at the efficiency of the power amplifier, it is also increasing with the output power, and it is at its best at the maximum output power. So efficiency means whenever you applied some power, some portion of that power is going into the output power. So the ratio of that is called the gain, and their relation is defining the efficiency, that how much power is converted into actually useful power. So of course if our efficiency is very low, then we cannot have full utilization of the signal. We are only getting some percentage of the power which we could have received. So of course we want our efficiency to be very high, but at very high region then we have the non-linearity there. So it becomes a compromise between two things. If you plot our efficiency of power amplifier versus linearity of the power amplifier, we can see this kind of curve which is tapering in nature. It means when we have efficiency very low, then linearity is very high, but as we keep increasing efficiency, linearity goes low. So we have to choose somewhere in between. So one method can be that we have to do the compromise, either we lose efficiency or either we lose linearity. Now if we lose linearity for the sake of efficiency, what is the problem there? Our data is getting distorted, because it is not the replica of the signal what we have proposed originally. So the data rate, it will fall down, because the data which is being received at the receiver, it is not a perfect data. Most of the data bits are distorted and they are not useful, they are not giving the useful information. So of course we need high linearity. In that case, to maintain this high linearity, we have to work in the lower region, and because of that we have to apply very high energy at the input, and it will lead to long talk time, and during longer talk time it will take more and more power, and the efficiency will be lower. It will lead to your high bill eventually, or high lower time of the battery usage. So battery will expire soon, because you are always taking more and more energy from that. So we want to have good efficiency as well as linearity. So let us have a look at the distortion parameters, how they actually work. Let us assume that our power amplifier, which is a nonlinear device, it is actually third order transfer function. So yt is a function of xt, and xt is the input signal. This k1, k2, k3 are representing the coefficients attached with the particular kernel, particular nonlinearity order, which are according to any particular PA. So what we do in the real life, that when we have the input and output data, we fit our k1, k2, k3 so that it is resembling the actual y of our practical power amplifier. So these k's are the PA model coefficients according to that. So let us see one example when we are applying single carrier signal. So our xt is actually just a sinusoidal signal which have one amplitude and frequency is omega, and it is being applied here. So when we do that, so third order PA, it is our assumption here. Our xt is a cosine function, so let us put that value in here. So our yt will become k1 k2 A square cos square omega t plus K3 A cube cos cube omega t omega 3. Now, if we expand these relations, and so the expression becomes this. So, if we collect our terms together for the DC frequency and omega t frequency and the higher frequency, you will have DC terms as so there is no frequency in this component, it is coming from here, and okay, it is just coming from there, sorry. So, only this is the DC term. Then we can collect the coefficient which is connected with our original frequency. And then we can collect the higher order terms. So, we have two higher order terms, twice of the frequency, which is K2 A square divided by 2 cos 2 omega t, and 3, no not 3, just K3 A cube divided by 4 omega 3. So, if you look at this expression, we will have 4 components from here. If we apply single sidereal signal, one will be at DC, one will be at our original signal frequency, one will be at second harmonic, and one will be at the third harmonic. So, we apply a signal which was at, and in frequency domain we had applied a signal which was at omega upon 2 pi frequency, and at the output, because of the nonlinearity, we are getting a signal which is having a component at 0 frequency, a component here which does not have the same amplitude, it has different amplitude than this one, and omega upon 2 pi, then it has some component at 2 omega upon 2 pi as well as 3 omega upon 2 pi, right. So, for one signal in the frequency domain we will see more than one components. Now, these components are very far, so you can say okay, we will filter it out and we can take this signal, but still if you look at this, our output is not exact replica of our input, basically it has some extra terms here. So, we wanted actually just this term, but this is the distortion term, this is term which is coming from the nonlinearity, this. So, this was the case of the single tone. We can from our eyes we can visualize that what will happen to different terms there. Now, most of the advanced communication system waveforms, they are multi-carrier. So it is more significant. So take care of two-tone test. We have to see the mutual interaction between the different tones here. So let us assume that we have two tones and they are situated at the frequencies f1 and f2, and we are assuming that f1 is at a frequency which is lower than the f2. Now we have two amplitudes, one is x1 and second is x2, and this is what we are representing here. 2 pi f1 we are representing as omega. So now instead of this we apply this two tone signal here. So when we apply this signal, still we are using this model of the third order. So yt, k1 is k1, and instead of xt we are using our new signal which has the amplitude x1 cos omega 1t plus x2 cos omega 2t. Now the second term is the same, but with the square term. So we will be opening the expression for this one. So this part will be intact. So it will be k1 x1 cos omega 1t, k1 x2 cos omega 2t. Now in this expression it will have expressions such as k2 x1 square cos square omega 1t plus k1 x2 square cos square omega 2t plus k1 2 times cos omega 1t cos omega 2t. Okay, it is k2, 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 k2. Now for the third expression, k3 will be there, and it will be x1 cube cos cube omega 1t plus k3 x2 cube cos cube omega 2t plus k3 2 times cos omega 1t cos omega 2t, and the bracket so it has x1 here and x2, and similarly they also have x1 x2 here multiplied. So we will have all these terms there. So we can simplify these. From here we can see that at the original frequency we are going to have these components. From here, similar to the previous case, we will have 1 plus cos 2 omega 1t. So we will have one DC coefficient from here and one at 2 omega 1 term. Similarly, here will be one component at 2 omega 2 and one DC component. This kind of term, you always know that when we are multiplying two sinusoidal signals, they give the frequency of omega 1 minus omega 2 and omega 2 minus omega 1. So it will be difference of these frequencies. These terms will give you this single tone term, which will give the distortion, and the term at the 3 omega 1. Similarly, the term at the 3 omega 2 and one term which will be added to this term. In this term, you will be multiplying them together, and then you will have the terms where you will have 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1 terms. So we are summarizing these terms in this slide and the output is shown here. So, DC term is basically K2 x1 square plus K2 x2 square, which is coming from here. If you open this expression, it will give you K2 x1 square and K2 x2 square. Now, at our first frequency, omega 1 frequency, we are having component which are actually multiplication of x1 and x2 both. So, linear operation of x1, second order of the amplitude of the first frequency signal, and the multiplication of the two amplitudes. Similarly, at the second frequency also, the amplitude is a function of the amplitude of the both the signals x2 as well as x1. Apart from these tones, we will be having our harmonics at 2 omega 1, 2 omega 2 like previous cases. Apart from that, we will be having our first order function at omega 2 minus omega 1 and omega 2 plus omega 1. Because it is third order, we are also seeing the third harmonic here. And apart from that, we will be having 2 omega 1 plus omega 2, 2 omega 1 minus omega 2 like components at the output, and we can combine them together and they will have this amplitude, which is again the function of amplitude of both the frequencies. So, in the frequency domain, if we have a look at this signal itself, let us say it was omega 2 by 2 pi and it was omega 1 upon 2 pi, it was 2 tone signal. We have seen from there we will have some signal at DC, we will have some signal at the original frequency omega 1 and omega 2, and we will have 2 omega 2 minus omega 1 so it will have omega 1, 2 omega 1 minus omega 2 divided by 2 pi, and some addition term is also there where the omega 2 omega 1 are being added together. So, it will be somewhere here, something like this. In fact, it will be much farther away, and then you will have 2 omega 2 terms, 2 omega 1 will be before that, and 2 terms, and 3 omega 1 and 3 omega 2 terms, and all those terms will be appearing here. So, as you can see, 2 tone signal has more higher number of distortion products here. Again, omega 2, 2 omega 1 minus omega 2 term and 2 omega 2 minus omega 1 term, it will be very much near to this one, because there will be very small distance with respect to each other here. If we see omega 1 minus omega 2 components summation, it will fall much farther here. So, basically if you put a filter here, then this third component has a tendency to come in the filter range, and the harmonics etc. we can easily filter out, right. So, this is how it will look in the frequency range. F1, F2, because of power amplifier they should have some gain, but because some of the power has leaked into some other domains. So, at 2 F2 minus F1 to F1 minus F2, the nearby components are these, and because the addition of these terms, it is 2 times here and 1 times here, it is called third order intermodulation. The frequency terms which are twice of the original frequencies, they are called second order intermodulation. So, basically F1 plus F2 terms, 2 times F1 terms and 2 times F2 terms, they are called second order intermodulation. The terms which are in addition, but they are summation of 2 times F1 and F2, it is again third order intermodulation. The third harmonic is also part of this one. The DC and F2 minus F1, they will be very near at the end. So, as I was saying, if you put a filter here, it is difficult to filter these components can be easily filtered. So, normally whenever you hear about the power amplifier nonlinearity, you will see that people are mostly talking about third order intermodulation and not much about other kind of modulation, because they are much farther there. So, if we look at the amplitudes here, at the original frequencies f1, f2, if our amplitudes were x1 and x2, at twice of the frequencies we get the x square function, second harmonic. At the near the DC and level, from the first and second we are having the x1 x square and x2 square component. At the first order, sorry, second order, because the summation of f1 f2, there are two frequencies. Second order intermodulation are, if they are of the this nature, f1 minus f2, then they are just simply the multiplication of these two amplitudes, whether it is negative, it is subtraction, or whether it is addition, it is just a multiplication of two amplitudes. The compression basically is seen in terms of cube function, x1 cube and x2 cube, and suppression is actually intermodulation of these two terms, which is x1 into x2 square and x1 square into x2 square. So, just at particular frequency you can imagine, you can have a intimate, you can have a guess that what should be the amplitude order if you know the original amplitudes. At the third harmonic, it is simply the cube of the original amplitudes. Now, look at the third order intermodulation, which are very important intermodulation products. At the negative frequency, whichever frequency is coming earlier in multiplication with the 2, it is having the square term and the other term is multiplied the amplitude of that is just simply multiplied without any power there. Similarly, in this case f1 minus f2 minus f1 should be there, and it is f2 square x2 square, which is related to the second harmonic. Similarly, here also whenever you have multiplication in the frequency domain, in amplitude you can see the power of that frequency. So, the nth order intermodulation component for n equal to odd will have amplitudes which are given by this formula. So, how we can use it? Suppose we want to calculate for the n equal to 3, because it is the important IMD term. So, let us put n equal to 3 here, 1 upon 2 to the power n minus 1. So, it will be 2 here, then 3 C 2, which is 3 plus 1 divided by 2, and k 3 and x cube. So, this will be the power of that. So, if we simplify this, it will become factorial 3, factorial 2, factorial 1. So, then k 3 x cube factorial we are opening, so the amplitude of third order intermodulation product should be 3 by 4 k 3 x cube, and this is what we are seeing this expression also. Third order intermodulation product, whether they are the third harmonic or they are third order intermodulation, they are using the coefficient of 3 by 4 always. So, with this we are finishing this lecture, and in the next lecture we will continue with this more specification which are based on this analysis. Thank you.